Okay, I think we can start. Let me introduce Mr. Egor Rogov, but I think it's not necessary. Egor is co-author of the most of the educational programs issued by Postgres Professional Company, and he is an author of lots of articles about Postgres SQL structure. And today Egor will tell us about the statistics in retrospective. Thank you. Good morning. I hope everybody woke up. You're lucky. My name is Egor, and I work in Postgres Professional Company in Educational Programs Department. We're trying to do everything to make progress accessible, and we're creating educational programs, courses, we're writing books. We have a small book, probably all of you saw it. If you didn't see it, just take it from our stand. Also, we're helping other authors to write books about Postgres, and recently we published the second part of the book by Mr. Novikov, which is called Basics of the Database Technology. Now we completed the second part and issued both parts in one cover. We also uploaded the PDF version on our website, and you can read it there, or if you like to read on paper, then even this month it will become available in the shops. Okay, let's move to the subject. I will talk about statistics today. Probably I should tell a few words why do we need this. Let's say we have a query on SQL language. SQL is a declarative language. We are not saying how we want to get the data, we're just describing the parameters of this data. And the query execution is done by the scheduler. How it does it? It creates different plans of execution of the query. It selects the best among them. To have the best one, it needs to evaluate these plans. What does it mean to evaluate a plan? Plan is a tree of nodes, and we need to evaluate the amount of resources or time which will be taken for execution of the query. And when we go to the upper node, the cost of the upper node means the cost of the whole plan. So we need to be able to evaluate the cost of the node. It depends on the operation executed on this node, but in most cases it depends on the volume of data which this node should process to get a result. So basically it depends on the number of rows. As often we have different conditions applied to the columns of tables. Usually we evaluate the selectiveness of these conditions first, and we determine which ratio of the rows, and we multiply it by the number of rows, and then we will be able to get the selectivity and cardinality of the number of rows. So they usually go together. What do we need to evaluate the selectivity? We need some information, statistical information about the data which we work with. At least the number of rows in the table, the distribution of data among the columns, etc. So this whole pyramid is based on the statistics. And accordingly, if we need a good plan of queries execution, then we will need a good statistics, because this is the basis. What is a good statistics? First of all, it's up-to-date statistics, because data changes in time, and the statistical data must show us the current condition. Otherwise, it doesn't make sense. And this is why we need a certain balance. On the one hand, the statistics must be quite precise. in order to be able to build a good forecast. On the other hand, statistics cannot take a lot of space, because if it will be too big, then the scheduler will consume too much time to process it, and the planning of the process will take too much time. So we need to find a balance. And I will talk about this balance mostly, and we will see how the search for this balance took place in different versions of Postgres from the beginning and until today. Of course, this is not what's necessary. Scheduler must be able to use the statistics, and it doesn't happen all the time. Statistics might be available, but it can be disregarded in certain situations. So we need a good developer who will not hide from the scheduler the statistics available. This is a mandatory requirement, but not sufficient. An example which I will use is weather in Moscow. I have a table and which stores the data for 10 years about the temperature measured in Moscow. Every day we have 8 measurements with 3 hours interval, and this is the average temperature month by month on this graph. If we look, yes, the temperature is a digit, and if we see how many times the temperature is encountered, then we will get such an interesting graph. Unfortunately, the color is not visible, but anyway. So we have like 2 humps. One is around 0 degrees because it's the most common temperature, and another peak is approximately near 14 degrees. This is the distribution of data which we have. Now we will see how different Postgres versions processed such a picture. We will start from the Postgres 95, which in 1996 became available in the community. It is clear that in 1996 something was wrong with the name, and this is why it changed. The Postgres is convenient because it has a guide, and guide remembers all the commitments from the 1996. We have all the hackers' mailings, and we are able to understand what happened in Postgres in the past. We can read the emails, we can even build the second version of Postgres to understand how it worked in the past. This is quite interesting. What happened in Postgres 95? A PG class table was available, and same as now, it stored the number of rows and the number of pages in the table. Sometimes it's easier to work with pages, sometimes with rows, so we store both. This is the basic statistics, which is updated quite often, and we recalculate the statistics whenever we need it. It allows us to evaluate only the whole selection, but we have some conditions which we apply to the columns, some predicaments, and of course we need the statistics for the attributes. What happened in Postgres 95? The number of unique values in each attribute was stored, and the minimum and maximum values were stored as well. They were called low key and high key. This is the minimum information, which was enough to work with even distribution of data precisely. For example, unique keys of these 3 digits to work. And if the distribution was uneven, then it became much more complex. How can we use the statistics? For example, if we need to evaluate the selectivity of one simple condition, then we take 1, we divide it by the number of unique values, and we get a ratio of 1 value. If we have a predicament as inequality, when attribute is less than a certain constant, then we can use a proportion and just calculate accordingly the ratio. It's quite simple. If we can re-evaluate selectivity of such a simple conditions, then we can evaluate the selectivity of more complex conditions created with nodes and quite simple formulas. Just I would like to draw your attention to the fact that these formulas means independence of data in different columns and attributes. If there is a certain dependence between the data, then the formula will give us wrong results, and we will see later what can be done about it. So this is how it looked in practice. We all know the tables of PG statistic, PG attribute. It was the same as now. Just a number of unique values was stored in PG attribute and not in statistics, and then it was moved. But there was one particularity. We had a field for these values, but Postgres did not field them at all. They were considered during the calculation, but they were not filled. So we thought that there should be some external script which would calculate these values and put in the system catalog. For example, inside the source you can find a script written in Tico which performs select distinct for each table and calculates the value of unique values in each column. And then it updates it in the system catalog. However, we have such fields, and if we try to understand what's happening, then we will see that in Postgres 95 had explain command, which showed just the names of the nodes. It did not show the cardinality, which we can see now in rows, nor the cost, just the names of the nodes. And it was quite difficult to understand what was going on. Plan was shown as notice and not as table as now. Using the formula, we can calculate the value, and of course they will be wrong because we have uneven distribution. You saw the graph with two humps, two peaks, and of course the scheduler will make mistakes. And there is another interesting fact. There was an error in code, due to which Postgres evaluated selectivity of each inequality is 1/3, and this error was found only in version 7.0 4 years later. So for 4 years we lived with this error. Version 7.0, year 2000. In this version we realized for the first time that there is a problem of unequal distribution, and we tried to do something about it. First we found a simple solution. We created specific statistics for one most common value, thinking that others will be distributed evenly. And another important change which was done, it's statistics for undetermined values. How to use it? The share of unequal values allows us to use the selectivity of predicate, which equals to the often value, and we take the ratio from the statistic itself without thinking too much. And if we need to evaluate something which is not equal to the often constant, then we can take 1, meaning all the values to deduct the share of often values, then to deduct the share of undetermined values, and then we need to divide it with something. We need to divide it by the number of values which we have, but Postgres did not collect such statistics. It was removed, and that's why we just divided it by 2. It's not the best choice, but at least it's something. How it looked like? We had a command vacuum analyze which collected the whole statistics in the database, and we did not need any scripts anymore. And the whole statistics was moved to PGStatistics in the same way as it's done right now. And we realized that the algorithm which was looking for the most common value was not the best one, because it was written for the case when we need just one most often value, or maybe 2 values. And in our case, this algorithm was mistaken, thinking that the most common temperature is minus 12 degrees, which is wrong, but it was its opinion. And here we also store the frequency, how often we encounter such a value. And null frag means 0 in this case. So what do we get out of it? It gives us, for example, if we want to look how many times we encountered minus 12 degrees, then the scheduler will evaluate the selectivity correctly, with correct result. In other cases, it will be mistaken. So selectivity for inequality in this version was corrected, and the formula gave us quite precise results. The next important version was version 7.2. It was important because the basic statistics was updated to the condition which we're using until now. We created an array of the most often values and the array of frequencies of these values. And for all the others, we created a histogram. It's a height-balanced histogram, which we calculated based on the certain number of bins, and the boundaries of each bin took approximately the same number of values. In this case, we store only the boundaries. We do not need to store the frequencies, because if we divide 1 by the number of bins, then we will get the frequency, regardless of which bin. If we try to represent it in graph, then the square of these rectangles will be the same. If we need to evaluate the selectivity of attribute which equals to more often value, then we just take the frequency from the array. If it's not the most often value, then we will think in the same way as previously. We will deduct from 1 the frequency of the most often values, and the rest we will divide by the number of non-unique values. Considering that the histogram is built in a way that it considers not the most often values, then we will have to calculate the most often ones, for which we know the frequency. If we need to evaluate the selectivity of inequality, then we will have to find the most often values which are equal to this inequality. Then we need to find the number of full bins which will be sufficient for the inequality, to take the value from them and to take the current bin where our value goes, and using the proportion to consider the part of this bin. I tried to write this formula, but it was too big for this slide, and actually it's not important because the scheduler will calculate everything by itself. We just need to understand the approach. So how it all worked? We have a command analyze separately from vacuum. We could tell to version 7.2 analyze, and we have a list of the most common values and the array of frequencies, and another array with the histogram boundaries. The minimum and the maximum value we don't have to store, because the most left shows us minimum and the most on the right shows us maximum. This is the statistics which gives us the absolutely correct forecast based on the conditions which we reviewed earlier. We have a lot to be desired, to be improved. The version 8.0, what has been done? It supports the collection of statistics for different types of data, because Postgres can be expanded and user can write its own type of data. That doesn't mean that the statistics which Postgres collects for dates, rows, etc. will be sufficient for your other types of data. Maybe you need other type of statistics, and maybe you should consider the selectivity in some other way. And we created a hook or callback, you can call it anything you want, which allows to attach the statistics to any type. Another important thing is statistics of indexes. They were available in Postgres 95, but the scheduler did not know if it should use this index or not, because it could not evaluate the selectivity of such a condition. For example, we take the month and we compare it with 1, for example. We understand that we mean January, so it should be 1/12 of all the values. But the scheduler doesn't know about it yet, and it's unknown value for it, and it evaluated the selectivity based on some predetermined ratio. And in 8.0 version, statistics by index became available. When we analyze the table, we get the correct statistics, and the scheduler understands if it should use it or not. In this case, it decided not to use it, because until the version 8.1, we had only 2 ways to address to data: index scanning or byte-by-byte scanning. And bitmap scanning will be available only in version 8.1. He thought probably that 2500 was too much for this scanning.
And now we're moving to the version 8.4 and 2009. In the previous version, 8.3, into the Postgres core, we have added the contextual search. It was always also there priorly, but in the form of a country. Now, what do we mean by full text search? We have an MTX vector that is an image of the document. So basically, it's just a list of lexems that are contained within the document. And then with the operator and 2 adds, we can compare the search to the request. And we need to understand how to evaluate how good is it. Here we are aided by understanding what words can be found frequently in the documents and what less frequently. Now, the next thing that we need is for the operator to be able to correctly choose the way in which it's going to function, because in essence it's a search within an SQL query. So there is a small optimization that you can do. If you, for example, you're doing a search engine with a frequently met word and a rare word, so you can either find the documents that have the rare word, the common word, and to intersect the 2 lists and to get the common results and show that as a result. But this can be inefficient. It could be more efficient to find those documents which have the rare documents which have the rare word, and to just cross-check if the common word is there as well. And this is going to operate faster. And so the statistics for the proper search allows us to do all of this. So in essence, we're just collecting the list of words that are present in the document and their frequency. So this is the kind of list we get. Usually this list is larger. I just condensed it to actually fit onto the screen here. But we can see that the most frequent words that we encounter, you see that the word road is one of the most commonly encountered. And here we can see who has written the most emails into the mailing list. The main difference from what we have had before is because we were trying to get the frequency of the meaning, and now we're trying to get the frequency of the actual words. And we understand that these lexical units, words or tokens, that this allows us to correctly forecast. And so in the previous version, in 8.3, when doing a search for the word road in the hacker mailing list gives us a small amount of results. In the version 8.4, is already able to understand this and to give the correct saying, and approximately 2/3 of letters contain this word. And if we are to try and add a token that we see more frequently, so for example, the word tattoo is mentioned twice in the hacker's mailing list, then we see that its amount drops significantly. If we are to be clever, it should be dropping to a 1, but, well, nevertheless, it still gives the optimizer a hint that in the second case you will need to go over the index, and in the first case you have to scan the entire table, because anyway you are going to have to look through the majority of documents. Then, in 9.2 was further improved in 2012. In this version, we've introduced the array statistics. With arrays, we have a similar story as we did have with documents. Various arrays are probably going to be unique, but the elements that they're comprised of are going to be somewhat alike with one another. So we can collect the most frequently met elements of the arrays, and then we get a histogram glean of these arrays. And this allows us to evaluate the objectivity of the conditions of two arrays intersecting, of one being part of another, and so on. And if we are to compare the previous version, for example, 8.4, it is going to give us the wrong results. Here it is done in the following way. The table, it contains one line for each day that we measure, and within this line we have an array out of 8 digits which represent the temperature that we have observed this day. And we can make a search query, we can make a query like find a day where we had 0 degrees. And version 8.4 just gives you the same value for any temperature. And version 9.2, using the statistics, can already show you fairly correct values. And in the version 9.3, this was further propelled, and they have created the statistics for various ranges. And for ranges, we essentially don't have any elements, and everything that is collected is just a histogram. The histogram of the limits of these ranges, and then the histogram of the lean ranges. And this also allows us to evaluate the selectivity. And if we are to use the same table, where you have a table per day, a line per each day, we can keep the range of the temperature changes on each day, and we can type in queries like, please find me the days when these ranges included, for example, 0 degrees or some other measurement. The previous version, 9.2, would provide us completely incorrect results, and version 9.3 is already able to provide us with fairly accurate results using these statistics. And slowly we've made it into the modern day. Postgres 10. Now, what was added? We have extended statistics that have been added. This is also multi-column statistics. Prior to this, all the statistics that was collected exclusively using one column and did not take into account the connection between the various columns. But now we have the ability to actually take that into account, and we can gather statistics for 2 or more columns. And we had 2 types of statistics of this sort. First of all is a search for dependencies between the various data, and this allows us to combat the problem of the correlating predicates, which I was talking about from the very beginning. And the second one is the amount of unique combinations of values of the attributes. Now, how can we use this? Just imagine that we want to store not just the day where we are doing the temperature, but the entire month in our table. It is evident that if we know what day it is, it tells us which month it is. So whether we write that it's going to be that month is equal to 1 or we don't, it does not affect the results, but the planner doesn't know this, and he keeps them all separately, and each condition decreases the amount of lines that, as the optimizer thinks, are going to be left in the search. But this is dangerous, because if we significantly lower the cardinality, Postgres can think that we do not have enough data and is going to start use nested loop indices, and vice versa. If the data is abundant, then, well, bye-bye performance. And the second option is we can say how many pairs do we have in total, how many days / temperatures. And here the planner is trying to guess the result, but he's mistaken, because he does not know how one is tied into the other. Now, what do? We need to create extended statistics. This has to be done manually by the team of Create Statistics. In the first case, we can create statistics like dbiensis between the day and the month, and in the second case we can create statistics like nlisting. This statistics is stored in a new table which is called the PG statistics ext. And this is how it looks like. So the statistics on the dependencies, it shows us that from the very first attribute, the second one is derived with the probability of 1. And at the same time, the Postgres has decided that there is no dependency, that no information should be present here. And for the amount of unique values, he just decided how many attributes we have and how many unique things are there. And these statistics allows us to very accurately estimate and evaluate these 2 queries. In the first case, instead of 1 line, we're getting 8, and this is right because we have 8 measurements per day, and in a single day we must have 8 units, 8 measurements. And in the second case, we can see that the value is also correct. And now Postgres 12. In Postgres 12, multi-column was further improved, and now we're able to collect a list of the most frequent combinations of values for the multi-column statistics. And now imagine such a thing. We want to look how many times in July we had 14 degrees. This is the first query. And the second query is how many times in July we had 0 degrees. Well, it is clear that we're probably not going to get a 0 in July, but the planner doesn't know this, and he thinks that, well, 0 is more generally frequent than the other one, so I'm going to spend more time evaluating it. And it thinks that 111 times we have 111 times with 0 degrees in July, which of course is not true. Now, when we're talking about, you can't just fight it with dependencies, because the dependencies are not actually giving us any extra information. And the only way we can deal with such queries is to collect pairs of values. If we're collecting together the month and the temperature, and to just store their frequency, which is exactly what has been done. The table of PG statistics X in the 12th version was halved. They have outlined the statistics X data, and in this data table they are storing the combinations of the most frequently encountered values. And why have they done this? Because the values can be spied on, and that's not very good. And so the data is hidden from the data table is hidden from everything. The X is an open one because you can just see the titles, which is why this was the case. Now we have two tables. And if before all these arrays of the values of the frequencies were all kept in simple text, then you can just view it with select. And now they decided to put this information into a catalog and binary, and thankfully there is a function that allows to decrypt this, which is PGMC list items, and we can see that here in the values we're storing pairs, and we are storing the frequencies with how often these pairs are encountered. So this statistics allows us to correctly understand how many times in July we had this temperature. And now if you see in the previous case you have 1 because the 1 is the lowest value one can encounter. Well, that's how our understanding of statistics changed. And now let me draw a conclusion and say a couple of words regarding how can we impact this and when there is a point in doing so. It is very pleasant that we only have one lever that we can pull, and that is the statistics target. And this value defines everything for us. First of all, it defines the size of the random pool that we are getting, which analyze reads in order to gather the statistics. In fact, the value that is written in statistics target is multiplied, and as a result of the multiplication, we get the amount of lines we need to analyze. It's interesting that this amount does not depend on the size of the table, and so even for the largest of tables, statistics is only going to be gathered pretty quickly. And this value also determines the size of the lists, so the size of the most frequently encountered values, the list of the most frequently encountered elements in the definitions, and also it's this value that determines the size of the histogram that is gathered. And so it's just one value, but it does so much, one digit. And why would we want to tweak it anyhow? Well, because when during an analysis we're getting a reading of a random range, random pick of pages, if your data are very unbalanced across the pages, you can run into a situation where you're doing analyze, get one numbers, and then run analyze for a second time, and then gets completely different image and understanding of what's going on because different values were read. And if the difference is so big that you have to alter your plans constantly, then you may want to increase the amount of pick-out range in order to take into account the larger amount of pages to get some stable result. And maybe you just want to have more precision to your range. And so let's say in some column you have 200 unique values that are being kept, and your statistics target value by default is 100, but you want to have exact numbers for all the 200 of the entries, and then you just need to increase this number to 200 and you'll get the fully accurate entries. But it's very important that fully accurate statistics is unnecessary, ever. It will always be slightly inaccurate. So if you are twisting this lever, tweaking it, then you're getting more accurate results. But if this does not impact your plans, then maybe this is a futile endeavor and you don't need to tweak it. Now, the next thing that you have is the extended statistics that at least for now needs to be gathered manually. Postgres by itself can't understand for which columns does it need to do. So this is the task of the administrator. But when you're creating the statistics, from here on out is going to be supported automatically. This is the very first thing that you need to remember if you have correlated data in your columns. This is going to lead to the mistakes in your forecasts of cardinality. Now, how is this set up? First of all, you have a parameter, default statistics target. You can change it on the system level, on the level of the database. But this is most probably not needed because the 100 value is generally, on average, is adequate. But this setting is very comfortable to be changed on the level of the actual running instance, and you can just put set, analyze, explain, have a look at the plans, and then just quickly evaluate how your change in statistics target lead to your plans changing. And the fact that you may want to do is to change the statistics target on certain columns. For example, if we're talking about tables, then it's done by the rotate tables command in statistics. If it's statistics on the indices, on their expressions, then you just do the filter index and statistics. And in 13th version of Postgres, you will be able to do the alter statistics, set statistics, in order to change the size of the list of these more frequent combinations of values. And in the current 12th Postgres, this is unfortunately undoable in this manner. Now, this is everything that I wanted to say. Thank you very much for your attention. If you have questions, you can ask. If you will have questions later, you can always write us an email. And the edu will be happy to answer. Igor, I have a question. This is just for interest. How does the statistics of primary keys and other unique columns kept? Why do you need histograms and all the other difficulties? I think in this particular case we don't have histograms. I think the enlisting is the values that you have, the amount of unique elements. It can be of two types. You either have a real value there, or you have some negative value, which shows the percentage of how unique it is. And for unique values, you always have -1. This just means that all the identifiers are unique and there's nothing else to do. Thank you very much for your presentation. Yes, I'm here. Yes, I can see you. Please tell me, is the statistics accounted for in the cases where we create a hybrid index like B3GIN? So, for example, our first column is going to be a normal integer, and the next one is going to be, for example, a full text or an array, or many things similar, or B3G, or so it's a hist. Well, the statistics for the two columns. Well, just look at this. Statistics is only related to the index only in the case where your index is built on an expression. For normal indices, we just evaluate the statistics on a specific predicted item, and then we're getting some cardinality into this. We're starting to try and understand, do we need this index or do we not need this index? How costly is it going to be to calculate a specific index? How costly is it going to be to perform the entire scanning? So it doesn't really matter what specific index you have built up. What matters is, will you be able to get the rows value? Well, my question here was in how useful was it using the index or to evaluate the amount of rows that you have, the lines you have. And as far as I understand, this hybrid indices, there are big mistakes in evaluations, even the large statistics we target, even with, well, not with the large one, sorry, the statistics of this table. Well, once again, this does not depend on the index. Here you must look at what predicates you're using and how are they evaluated. The index has nothing to do with this. Yeah. We're talking about how generally useful is it. Thank you. Good day. Thank you very much for the presentation. And the fact that we can collect the statistics, order the collection of the statistics by ourselves is great. example, me as an administrator of the database, I will try to analyze the database. I will try to set up the statistics, but I'm guessing that the collection of statistics by itself is fairly demanding. Moreover, taking into account that it's a process that requires a certain time, puts some load on the resources, and then the resources themselves are architectural, so we're loading the weakest link. Can you please give some recommendations in terms of how can we correctly evaluate the general slowdown of the system which is caused by the collection of statistics? How can we collect the statistics correctly so that a system that is going through high load cannot make the situation worse, but at the same time to maintain the selectivity of the ranges that are being picked out in the optimal state? Well, in my memory, I don't think anybody complained that statistics collection would somehow be significantly influencing performance. Well, vacuum, sure, because it's constantly reading, but statistics is not reading that many lines, so its effect is not as pronounced, it's not as dramatic. Excuse me, then can I also clarify, after vacuum, is it much easier to collect statistics or not? Or is this unconnected? Yes, they're independent of one another. Yes, but does it somehow mathematically impact the speeding up because you have the putting pages in order and stuff because we're in a physical system, right? No, in an analysis, we're working with a random range of page selections. And it can affect if you had a lot of deadlines in the page, or maybe the analyzer will have to read more if it has to find the ones that are currently alive, but I don't think it really impacts it. Here, the thing is, the entire thing is in setting up the auto-analysis. There are a number of settings, parameters, which are very well known, and in the cases where you think that your collection of statistics is going to somehow affect performance, you can play around with the statistics, but I think that it's not what you need to pay your attention to, at least not right at the start. And can I ask one more question? Is there some analog of system statistics in Postgres if we are going to draw a parallel with Oracle? Is the current productivity of the physical surroundings taken into account? No, it's not taken into account in any way. Hello. Hello, one more question. For example, we have a varied table. A table are changed significantly in data. If we're collecting the outer collection of data, will we be able to dynamically change the patterns for collection of the statistics? Well, there you can set it up the following way. You can just write the amount of lines that need to change since the last time statistics were collected. That's the only thing you can use. So they don't have, if we have an unequal distribution and we change an n amount of data, and I know that the data for the non-equal redistribution is going to be made part of it, so there's no way I can script what percent of the table are we actually going to be using for collection. And no, this is all set with the parameter of statistics target, and that's it. With the redistributive analysis, well, analysis will deal with that. It looks at which data is present and is going to read it. So, well, I think that it is time to round this off, and now let's ask the last question. Okay, fine, the one before last. Now, as far as the multi-column statistics go, is there an analog for JSON-B, and can we use combined statistics like multi-column from the regular columns, and for example, with the keys of JSON-B? Well, we don't have anything for JSON-B. Well, we can't. We have no way of getting inside JSON-B. We don't go into it. I mean, we could come up with something, but we haven't yet. Like, we're collecting just general statistics, but I don't think that is going to be very clear. Thank you very much, Igor. My question was already asked, and I can only repeat that all the non-relative, non-related structures like JSON, B, Astona, that they do not contain they don't have statistics collected on them. So what is going on inside remains unknown. Yes, but we have the opportunity to gather the statistics for any type. So if you come up with a method of how we can logically collect statistics, we can implement it and we can make it part of Postgres, no problem, but nobody has come up with the way yet, so. Well, thank you very much, Egor, everybody who has been here. All those who want to ask questions, ask Egor questions, please catch him off stage.